Hello everyone. Today we are going to learn another tool which can be used for the assessment of three-dimensional structure of mutated proteins, and it is known as Swiss model. Swiss model includes the Swiss model repository and the Swiss model workspace. It is the automated protein structure homology modeling platform for generating 3D models of a protein using a comparative approach and database of annotated models for key reference proteomes based on UniProt KB. It is easy to use web-based platform processing over 2 million model requests per year, providing model information for experts and non-specialists. So first of all, you will Google it, or you will directly click on its link and will click on Swiss model, and this will open the home page of the Swiss model. Then click on start modeling, and it will give you a space for pasting your target sequence, and then you will paste your amino acid sequence here. If on pasting the amino acid sequence, the sequence turns colorful, it becomes colorful, it means that it is suitable for the further analysis using Swiss model. It will be easy, it can be a target for the Swiss model analysis. But if it doesn't turn colorful, it means the Swiss model cannot process it for further analysis. Now, as I told you earlier, that it is a homology modeling server, so it can only interpret the 3D configuration of your Curie protein if the Curie protein has more than 30% similarity with any of the already reported proteins. And the already reported proteins means the protein with a known ID, and its 3D structure has also been predicted and is stored in the PDB protein database. So in order to now first we will search for the templates in order to know that which is the protein with which it is our Curie protein is showing the best more than 30% similarity. And then when you will perform the template search, you will see the whole sequence flowing in front of your eyes, which means that the tool is actually performing the blast analysis of the Curie protein. It will take some time, and after that it will show all the templates. You can see here that it has predicted 50 template molecules, and the structure of the very first template is shown here. I have selected the very first template, which is shown in sky blue color, and now we will select that which of the template is most suitable for building the model. For that purpose, you have to check some of the parameters which are given in above the selection of above the selected sky blue area. You can see on the left side there is coverage, and then there is GMQE score and method and ligands. So first of all, you are supposed to see at the coverage, and you can see that in first 3 templates the coverage is maximum, which is shown by the blue colored area. And then there is GMQE score. GMQE score actually stands for Global Model Quality Assessment, Quality Estimate. Its value ranges between 0 to 1, and if it is closer to 1, it means the structure is highly reliable, but if it is closer to 0, it means the structure is not reliable, and this template cannot be preferred for building the model. And then there is identity. The identity or the coverage is 92%, which is also very good. We were expecting only more than 30 or 40% similarity, but here the 92% similarity is obtained, which is proving the quality of this template for further model building. And then you can see in the parameter of method, under the method there is written X-ray. It means it shows that this template, the structure of this template has been predicted through X-ray crystallography, which is experimental method of predicting the protein structure, and this structure is saved in the PDB database, so which makes this template more reliable. Actually, the homology modeling, it is very easy. It is comparatively easier to predict a three-dimensional configuration of a protein using the homology modeling as compared to as compared to the ab initio methods, because it increases the confidence level, our confidence level on the predicted model. Then you will click on the build model after selecting the required template, and this is the model which has been built by the Swiss model on the basis while using that the template which you have selected. And then you can see here the 3D structure of this of the Curie protein. Curie protein, at the same time you have to consult on the left side the GMQE score, and which is which is also preferable because it is closer to 1. Its value is 0.94, which is very good value. And then there is Q mean score. The Q mean score is also very important parameter in considering any model for any further analysis, like docking analysis, or if you want to retrieve, if you want to use this predicted protein model for any further analysis. Most commonly we use it for the docking analysis, so it will be favorable for the downstream analysis if you or for the further analysis if its GMQE and Q mean scores are favorable or in good, or in good, they fall in good range. So as I already told you, that GMQ is perfect, Q score is perfect in this case, but Q mean score is actually stands for quality model energy analysis, and its value is given, which is given here, is 0.92. But actually if its value is around 0, it means this value is ideal. But its value, if its value is q mean z scores value is below the 0.4, minus 0.4, then it means that the structure will not be preferred, cannot be preferred for the for the docking analysis or any other further analysis, because actually it shows the quality of its atoms and bonds which are not good enough that it can be used, so it cannot be used for the docking analysis. Now you may select the option in for the representation of its structure. If you want to use its cartoon form or tube form or trace form, or suppose if you select the lines, then you will see the structure, this structure in the lines format. And next is what is important is the graphical representation of the quality of the z score, which I already told you. Q mean z score should not be around below the minus 0.4. And for that purpose you will see this graph. This graph is showing you the a dark colored area, and there is a red star, which is your model, which is actually your model, and your model should fall in this dark colored area. It should not be beyond it, like it should not fall in the white colored area. If it falls, then it will not be preferred for the docking analysis or any other analysis. So here you can see that but unfortunately the Q mean z score given here is minus 0.57, and the position of our model is although it falls in a dark area, but not in the in the good range of the z score. So we can show this structure in, we can select this structure in order to see the effect of mutation on the 3D configuration of protein, but we cannot prefer it for the docking analysis or any other analysis. Now the question is, how can we represent the data which we have retrieved from the Swiss model? Here is a figure which I have selected from one of my published article, and you can see here the multiple figures of 3D configurations from A to K. A is showing for the normal, and B to K are showing for the mutated protein structures, and you can see here that the D and E case has in case of D and E, the SNPs have considerably altered the structure of the protein as compared to the normal one, which is shown in A. So this was all about the Swiss model. I hope you would be able to perform this analysis in a better way. Thank you so much.